happy to be here, and then know also that I have a lot of excellent speakers behind me. So I'll try to kick us off and give an overview today, and hopefully set us up for some great discussion and hearing from other experts throughout the day. So to get started, I'm at Colorado State University, and just so if you're not familiar, Colorado State has made a really unique investment in this group called AgNext. So it's an initiative that is basically a joint effort between the College of Agricultural Sciences and the Veterinary Medicine College there at Colorado State University. What's unique is it solely is focused on sustainable animal agriculture and trying to tackle this issue from a standpoint of all facets of sustainability. So not just thinking about the environment, but thinking about the social and economic aspects as well, and trying to come up with practical solutions that actually scale and address these issues in the commercial industry. Sorry, it's not advancing. Might need to just advance the slide. Thank you. Oh, perfect. So from that standpoint, there's a large team that is a part of AgNext, and most of these folks on this slide here have just started working in the past year. So myself, I just started with CSU in end of August this past year. But as you look through this list of expertise, the key thing here is that we have folks with life cycle assessment modeling expertise, folks with animal science and animal nutrition expertise, from both the dairy and a beef perspective, more of a rangeland ecology focus. And what's super unique about our group is we also have communication staff that help us communicate this out to stakeholders and really be key to that land grant mission of extending this knowledge out into the industry. So the topic of the day, when we think about sustainability, this is not something that's surprising to you all. All of these issues, whether it's human health, human nutrition, animal production issues, ethics, climate change, all of it is kind of converged now in this muddled mess of sustainability, right? And this is part of the challenge that we're dealing with, is where to address some of these issues and how to advance our understanding, especially when a lot of these conversations are driven by value judgments as well, right? So there's a role for evidence and there's a role for understanding that some of these issues are challenging to address head on with only science, right, from that standpoint. When we think about this broader discussion, right, some of those headlines that I just shared, right, things about dietary change, et cetera, we know there's, of course, policies that are driving a lot of this conversation, but there's also a huge movement within the investor community, within the business community, so-called ESG, right? If you all have heard of that, especially in the last few weeks, it seems like it's been in the news a lot more, right? Environment, social governance. This gentleman on the slide here is just an example of what's been driving this conversation, right? So this is Larry Fink, the CEO of BlackRock. These quotes here are from his annual letter to CEOs from last year. If you're not familiar with BlackRock, right, they're the world's largest hedge fund. You can see they have a small amount of money of assets under management, right? So they're very powerful in terms of what they say, right, has ripple effects in terms of access to capital, right, and who's going to be funded in the future, right? So I think, again, this quote is very interesting. We focus on sustainability not because we're environmentalists, but because we're capitalists and fiduciaries to our clients. And thinking about it from a standpoint of this whole conversation around net zero, it's an idea of, are you going to disrupt yourself and achieve net zero as an individual industry or a company, or are you going to go away, right? From that standpoint, fairly straightforward, but that's kind of the mindset that's out there. So in response to the Paris Climate Accord, in response to this pressure that's out there, there's been many companies that have made commitments around net zero, climate neutral, carbon neutral, whatever the verbiage is. And we could have a whole nother discussion on that. Dr. Mittlener is here. He'll probably hit that one, right, in terms of what these different things mean. But the key thing is that just as you look at these different brands that are up here, a lot of them have an effect on animal agriculture, right? They have animal agriculture in their supply chain. Why that's also important is that most of these companies have made commitments that are inclusive of all three scopes of their emissions. So if you're not familiar with this terminology, this is pretty standard for the corporate world of thinking about emissions in different scopes. So scope one is your emissions that come from your own four walls of your own operation. Scope two emissions are emissions of energy that you purchase, right? So if we think about an example of, say, a packing plant, right? The emissions from within the own four walls of that operation and then energy that they use to run that operation would be their scope 1 and 2 emissions. Scope 3 emissions are inclusive of everything that goes into the production of a product, even everything from like employee travel, for example, could be included in a company's Scope 3 emissions. But if we think back to that example of a packing plant, Scope 3 emissions would include all the impacts of producing cattle, right? Everything from feed production, everything that it takes to get those animals in the door of the facility go into Scope 3 emissions. And so the reason I'm telling you this is, again, most of these company commitments have been made inclusive of all three scopes. And I think this is our challenge as scientists, right? Is there's a huge ambition and these commitments that have been made, but there's many questions around what actually are you measuring? Can you measure? What is your baseline? Is it accurate? How are we going to mitigate these emissions in significant ways or increase soil carbon sequestration in significant ways, right? So again, that's the background of what's happening in the corporate world. There are different entities in which these companies will disclose, right, or report their emissions or disclose other aspects of sustainability too. So it's just as a background of that's what's happening, right, in the broader community, right, from that standpoint in the business community. So if we get back to it, right, of the science of it, and we think about greenhouse gas emissions, again, I'll be brief on this because I know this will be covered a lot more in depth later. But of course, the three main greenhouse gases that we care about from a standpoint of the climate impacts of animal agriculture and how this fits into Scope 3 commitments for different companies and the broader policy discussion, those three greenhouse gases are carbon dioxide, methane, and nitrous oxide. So these gases have different potentials to trap heat in the atmosphere, different radiative forcings, and they have different atmospheric lifetimes, right? So traditionally, in these ways of accounting for greenhouse gas emissions, GWP 100 or the 100-year global warming potential has been used to compare these different gases. And it's pretty much a standard when we think about accounting in the US EPA inventory or company disclosures, right? And so in that scheme, right, carbon dioxide is the the reference gas, and so has a global warming potential of 1. Methane has a global warming potential around 28, right? So 28 times more potent over a 100-year time frame, and nitrous oxide 273 in this latest IPCC report. And then on the right-hand side, right, I've put the rank in terms of importance for global animal agriculture, right? Which one of these gases is dominating? And so to build upon that a little bit more, the UNFAO has a model called GLEAM, right? And they have updated this, and this is just some information from their dashboard of what's publicly available, right? So what we're looking at here is just the distribution of what is estimated as the 6.3 gigatons of CO2 equivalents that come from global livestock production. So as we work from left to right, of course, we have it designated in terms of what type of animal these emissions are coming from, right? Cattle, chicken, pigs, buffaloes. In the middle, what phase or what source is coming from. So as you all can look at this and see, right, enteric fermentation or the methane that directly comes from ruminant production, right, and has a lot of implications for what we're talking about here today with animal nutrition, is the largest source in the world. And then on the right-hand side is those different gases based on the actual global warming potentials that are seen down there at the bottom, right? So the key thing here is that around 11% of global emissions come from animal agriculture, right? It's not the single largest source. We know that energy is more important, but it's 11%. And what can we do to actually reduce that total amount of greenhouse gas emissions, right? And if we think about that middle portion, we can kind of bucket our opportunity into a few different buckets, right? For ruminant agriculture, enteric fermentation is the biggest opportunity, right, to reduce. Manure emissions are also a large opportunity. And I'll show you with the US data, could be a little bit bigger opportunity in places like the US and for certain production systems. Feed production is another big bucket, right? And I won't really hit on that too much today, but whether it's reducing emissions from feed production or increasing soil carbon sequestration, right? That's another one of our huge opportunities within animal agriculture. It's not necessarily directly related to the animal, but has implications for, of course, integrated systems. And then finally, energy use, which isn't that large of a source, but is important in terms of also mitigation potential. So that's the global picture. What about in the US, right? So if we look at the draft US EPA inventory that came out, just reiterating what I said, right? The vast majority of greenhouse gas emissions is seen on the y-axis here in million metric tons of CO2 equivalents. The vast majority come from energy production in the US. This is very true for most post-industrial countries, right? We burn a lot of fossil fuels. We all probably flew on an airplane to get here, right? This all adds up, and that's where the majority of our emissions come from. But if you look over to the far right, agriculture, and then this other acronym, right, that stands for land use change, and forestry, added together in the United States, they're actually a net sink. We don't typically talk about it that way, right? Globally, if you add land use change, forestry, and agriculture together, it's a net source, right? So this is another one of these distinctions. It depends on where you are in the world, right? United States, we deforested everything, 200 years ago. So now we're reforesting. So it looks better for us as compared to other parts of the world. They're still undergoing that transition. If we were to zoom in a little bit more on that 589 million metric tons of CO2 equivalents from agriculture. Sorry, my thing is not working again. Perfect, thank you. If we were to zoom in a little bit more and say, okay, let's try to break that up. Where are these emissions actually coming from? In the middle here is just a designation in terms of direct emissions. Are they coming from animal agriculture in terms of enteric methane and manure emissions? Or are they coming from crop production? And so you all can see those designations there. In the United States, nitrous oxide from soils is actually the #1 source of emissions, right, in agriculture, with enteric methane being the second largest. What's key is these are direct emissions. Of course, if we think about it from a life cycle perspective, a good chunk of that crop production emission bucket, right, should be allocated to animal agriculture because it's there to support animal agriculture, right? That's feed going to animals. But that's really the breakdown. And again, if we think about it, what's the opportunity? Well, we can see obviously soil nitrous oxide really matters, but so does an enteric methane, right? From a standpoint of can we reduce it and make an impact in terms of the lowering the total contribution. Perfect. So if you think about the trends over time of those direct emissions, what's happened since 1990? What's key is that even though, and I'll show on the next slide, right, we've reduced emissions per unit of product, it's always important to keep in mind that those net zero commitments and everything I told you about, those require absolute emissions reductions, total emissions reductions. And if we look at the total emissions coming from animal agriculture, they've increased, right, over time. So 43 million metric tons higher in 2020 as compared to 1990, which is, if you give you a frame of reference, Ireland emits around 60 million metric tons, right? So that's about how much that is, right, from that standpoint. Really, a lot of that increase has come from swine and dairy, right? And a big part of that is manure methane emissions. As those animals have transitioned and been consolidated into larger operations, we have regulations to protect water quality. We have more anaerobic lagoons, right, and storage of manure, which is good from a standpoint of applying manure at agronomic rates, but has led to more methane emissions, right? And this is, as I just referenced, right, emissions per unit of product, if we look at those three big ones, right, milk, beef, pork, have actually declined over time, right? Our production has increased greater than our emissions. That's good. We've decoupled, right? We need to continue to do that. But back in that context of achieving some of these goals around climate neutrality, total emissions reductions, we need to decouple further, right? We need solutions that actually reduce emissions at a greater rate and to drive down total emissions, not just emissions intensity. So on the enteric methane side, again, knowing that we're going to have a lot of experts talking on this, just a summary, right? Things that are known probably pretty widely in this room in terms of potential impacts on enteric methane, since that is the biggest chunk globally and in the US. Ways that we can think about feeding management, diet formulation, right? Thinking about ways that we know have an impact on ruminant methane emissions, whether it's fat, for example, or processing of feed like steam flake corn versus dry rolled corn. We know those things have an impact. And of course, the interest in potential feed additives and other ways to manipulate rumen fermentation, potentially, hopefully create win-wins from a standpoint of increasing energetic efficiency of the animal and decreasing methane loss from the animals per day. And one thing I will say, I think one of those other key aspects that's a potential, right, is genetic selection. And one is just to drive this home. This is just preliminary data from our research site at Colorado State. This past December and January, we had about a couple hundred animals in there. And these are just some of the steers that we measured daily methane emissions, feed intake, and body weight gain on these animals, right? And all I've highlighted here is just if we look at dry matter intakes in pounds, but if we look at dry matter intake versus methane emissions and based on gain, I've just highlighted two of these steers, right? They gain pretty similar. They have fairly similar feed intake, and yet they have a 24% difference in methane emissions, right? Which is kind of equivalent to, that would be a really exciting feed additive that reduced methane emissions 24%. And that's just the variation that we see in appendix cattle. They're actually all pretty similar. These are all from the Rouse Ranch in Wyoming for our CSU facility, right? So I think this is one of those frontiers as well, is now that we have larger scale facilities where we can collect methane phenotypes on a larger scale, what can we do from a standpoint of genetic selection in addition to direct manipulation of rumen fermentation through feed additives or feeding strategies, whatever it may be, right? Can these be synergistic opportunities? And since the title of this was opportunity, I also think it's important to bring it back to the business side of it and how will any of this actually change, right, in the real world? And I think this is one of those things of getting producers to think about this, livestock producers, but then also companies, right? What is the opportunity on the table? So these are just some napkin math numbers, right? So to give you some idea of what we're looking at here, just looking in the US, beef and dairy cattle in 2021, what were the methane emissions in terms of million metric tons? And then a scenario, what if we had a market penetration of 25% in beef cattle, just knowing we have more extensive animals, harder to get delivery of any sort of solution, and 50% in dairy cattle, some sort of technology that reduces methane 40%. If we put a carbon price on that methane reduction of $50 per ton, right, which is, just to know, definitely higher than where we're currently at from a voluntary carbon price, but at that level, right, you can see combined we're generating over $1 billion of revenue opportunity, right? Now, how that market gets facilitated, how that revenue gets shared, executed upon, et cetera, right? Those are all questions that we need to answer. Very important questions. But I think that's the important way to think about it is methane reduction opportunity is a large economic opportunity within the livestock industry as we have all this focus on reducing methane emissions. This other little box that I put over to the side, I think the other key thing about focusing on reducing emissions is so attractive and not to muddy the waters on soil carbon sequestration, right? That's a great opportunity as well. But if you follow that space, you know, it's really hard to measure. It's really hard to show additional carbon sequestration and to say it's permanent, that's going to last 100 years or more, right? When we think about enteric methane emission reduction, this is reduction of emissions. If they didn't get emitted today, it's never going to get emitted, right? It's a permanent reduction. And if it's a new technology, it will be additional, right? So I think from a standpoint of carbon markets, that's where enteric methane emission reduction, as we accelerate in that space, will be a very attractive opportunity, right, for the industry. So that's all the climate side of things. Again, we have all these ambitious goals. We know some of the science, but we don't have a lot of practical solutions, right, that are out there in the industry right now. That bigger picture, if we think about at the end of the day, right, we're still trying to nourish people. We need to think about feed food competition, nutritional security as well, right? So we all are familiar with these global population estimates, and I think that's been said ad nauseum, right? In agricultural circles, we got to feed 9 or 10 billion people by 2050. And I think it's interesting if we really look into the data of where we've been and where we're headed for population, right? This is with a FAO data here of looking at rural population versus urban population, right? And you guys can see I've kind of pulled out urban past rural back in the mid 2000s. I think that's a key milestone, right, of that urbanization trend that's happening in the world. And we know that matters from an animal source food perspective. Typically, people are moving into higher income brackets. They're going to consume more animal source foods, right? That drives total demand in this space as well. But what's also interesting is, of course, global population is growing, but now it's growing at a decreasing rate, right? And I think that's always important. It's not an exponential growth curve at all, right? We basically have a 20, 30, 40-year crunch time, if you will, if we're going to put a lot of pressure on our natural resources as we go through this. And then we're going to transition to declining world population, which I always kind of joke, that's a problem for the next generation, right? We're all going to be gone. Doesn't matter. How do you have a global economy and a declining world population? We don't have to worry about it, right? But at least in the near term, this is our big challenge, right? How do we do this in a sustainable manner? And of course, what's happened is animal agriculture has responded, right? So this is some trends I should say, in terrestrial animal protein production, right? Just to know the aquaculture folks that I'm not representing the trends in that growth. But what we're looking at here is metric tons of meat production of different types over time. And so this is a key thing too, is that there's so much to debate, and we'll hear that later about ruminants versus monogastric animals. And I think it's always important to ground ourselves in the reality of ruminant meat production is growing at a slower pace than global population, right? There is less ruminant meat available per person in the world. That's reality. That will probably continue because of the supply side realities of producing ruminant meat, right? So we have gone from beef being the dominant protein in 1961 in the world to now chicken, right? And this is kind of this dance between poultry and chicken, is a dance of two competing, right? Animal disease outbreaks, right? African swine fever and avian influenza. We'll see who's on top in the next couple of years, right? But those two are by far, right, going to make up a larger stomach share, if you will, in the future. So with that said, what are the implications from this feed food competition standpoint, right? So this is probably something that's quite familiar to you all. This is analysis that was done by the UNFAO in terms of looking at the climate impact of livestock production, but then also thinking about, okay, well, what are those feed inputs that go into livestock production? And so if we think about it for all livestock species together, of course, 86% of what livestock consume is not necessarily directly in competition with human food. Of course, the land use piece is a little bit more complicated, but that statistic, right, is I think pretty interesting and powerful. Of course, it's also different between ruminants and monogastrics, right? Ruminants have a much higher human inedible feed input as compared to monogastric animals, right? So this is important from a standpoint of thinking through where is that growth going to come from, additional growth in the next 20, 30 years, and how much strain is it going to put on human food supplies, right? And I haven't presented it here, but you also all probably know we are producing more calories per person in the world, right? So energy supply, hard to make that argument, I think, at times, that that's really the rate limiting step. So when we think about this, we can think about conversion of feed resources in a few different ways. One, I've pulled this out because I think this is one of the first references I've seen to this of human edible feed conversion, or trying to think about like net protein contribution from that standpoint, if you all are familiar with that type of work. So this is a summary from Bywater and Baldwin in 1980, right? This quote is still true today, right? A fundamental issue in terms of efficiency is how it's expressed, right? The ultimate concern is total human food production. And so they were making the argument here, it seems rational we should calculate animal efficiency in terms of human edible inputs and human edible outputs in terms of energy and protein. And again, we still see that argument today in terms of dry matter conversion efficiency versus energy, calories, whatever it may be. So as you're looking at this table from this report, right, basically we have the main commodities here of meat, beef, swine, poultry, and on the left-hand side is total energy, right? So just total calories in, calories out, protein in, protein out, not considering is this feed stuff that's going into this animal truly in competition with human food or not? And then on the right-hand side is a human edible energy and protein return, right? So again, this analysis back in 1980 for ruminant species, and milk looks good here, right? From both an energy and a protein perspective. If you look at the P column there, right? In terms of efficiency and percent, these systems are returning a higher percent than they are using. Right. And of course, how is that possible? Because they're ruminants, right? They're using non-protein nitrogen sources, protein sources that are not in competition with human food. Microbial protein synthesis allows, right, this ratio to exist. But even our monogastric species, right, can look better than advertised, right? From that standpoint of using feed inputs that are not in competition with human food. Now, the question with this, and we were having a conversation last night at dinner, right, of the whole, like, can you use only leftovers, only byproducts for animal source food production and not have any competition? Probably not, right? There's going to be probably some sort of optimization there of using human edible inputs and not. And so this is just an example from a nice study that was done at Kansas State, where they looked at dairy cows in an experiment, had two different diets. And so these two diets that are up here is just the control versus an eco diet, right? They're trying to minimize all land use competition and feed food competition. And when they ran this experiment, right, if you look down at the bottom, human edible protein return, incredible, right? These animals are producing, basically most of the protein they're producing is protein that wouldn't have existed in the world without them, right? Because they're not competing for those feed resources. But I've highlighted also milk yield, right, which declined, right? So this tension of how do we use ruminants for what they're good at, or use livestock for what they're good at, which is this upcycling service, right, of taking things that are not in competition with human food or land or feed resources, both of those perspectives. But how do we do so in a way where we're still trying to optimize total production? Because we still have that crunch period, right? We still got that 20, 30 years where we had to produce more total food for more people. So to that perspective, or from that perspective, right, I think that's one of those key things, key areas to focus on, even from a research perspective, is this whole idea of circularity, which is nothing new in agriculture, but it's a new word that is used in the corporate world, right? That sounds good, of recycling and using nutrients and energy flows in ways that make sense within the system. So this is just, right, a simple idea of thinking about how food, fiber, biofuel systems are connected, right, throughout that whole system. And of course, what's unique about those ruminant systems is they're basically bringing in energy and protein resources from range lands, right, from pasture lands, or we don't have access to, right, from a human perspective without them, right? But we can add on top of this, we could think about ecosystem services, right? What about grazing in Western lands to reduce fine fuels for wildfire suppression, right? Other aspects, other services that can be layered on top. And I think that's one of those challenges within sustainability is it's hard to put all these different aspects that could be important to us together in one experiment, in one metric, whatever it may be, right? So to that end, we were kind of given the task of, well, what's next? What are the needs out there, right? So when we think about sustainability, pretty traditional, right? We think about those three pillars: economic, social, environmental, and we think about a long-term perspective. And there's such a whole host of issues that could fall under that, especially when we think about animal agriculture and a sustainable food system. And so really our challenge from a research perspective is how do we do more of that systems type work? And especially within the confines of the funding that's available, right? And the realities of, you know, an untenured faculty member, you got to get publications out. You can't wait 10 years to publish this cool systems paper, right? So how do we work against those tensions from that standpoint and address these whole systems issues that really focus on those nexes, right? Those areas of overlap, understand where are their synergies and where are their trade-offs in these different aspects of sustainability. And I think that circularity component is very, very important, right, as we go forward to broaden our thinking beyond just carbon, right, beyond CO2 equivalent emissions, but also think about water, think about the resource competition in other ways, nitrogen from a reactive nitrogen basis. And finally here, right, just recognizing the role of value judgments, the uncertainty in this process. You know, a lot of us, we're scientists. We wish if you just told somebody, you know, here's the facts, they would change their mind, right? But when it comes to food, everybody's really an expert, right? Everybody eats. And a lot of these questions around sustainability, they're should questions. What should we be doing? What should we be eating, right? Should animals be in a sustainable food system? And should questions can never have a perfectly objective answer, right? And so I think it's just recognizing that piece of it as well, that one, we need a lot more social science, right, perspective when we think about these issues. So what are the gaps? I think I'm really going to focus here more on that climate piece of this, right? As I shared with you, we have a lot of aspiration out there right now. A lot of companies have made net zero commitments. They may have made them thinking there are no consequences, but you know, you may have seen, right? There's proposed rules from the SEC about disclosure and showing progress against these goals for publicly traded companies. So they probably will have real teeth, right? Some of these commitments that have made. But what is the gap between aspiration and reality, right? I think we can kind of summarize as one, we need solutions that actually have good efficacy, right? I think on the manure management side, we've seen progress, right, with reducing methane emissions from manure systems. That's awesome. There's market solutions that are starting to work there, but on the Enteric side, there's not a lot of solutions, right? And then again, that's our number one source here in the US and around the world. So we need solutions that work, and we need to think about them in all the different production constructs and contexts that matter, right? And I've kind of highlighted here, I think that always that underlying question is we do a lot of research to just find, the effect size that we care about for methane reduction, but then we're not thinking about, well, where's the energy going in the animal, right? Are we actually capturing it in a practical way? If a commercial feed yard that has 100,000 head feeds this thing and it costs 10 cents per head per day, we better find some real ways to pay for this, right? And I think that piece of it is kind of missing in a lot of these current research that we have. And so to that point, right, the economics, I think that's a huge question. We could come up with wonderful economic or technical solutions, but if the economics of this do not work, then we won't be able to shrink, right, the 138 million metric tons of enteric methane in the US. So key there, and I think that's where the modeling piece comes in, right? If we think about models to get more accurate, that's really important. But we also need to think about how could this be commercially deployed on an operation, right? Given the production metrics that a farmer or a feedlot operator, right, is actually going to be measuring, how do you integrate that into their system more seamlessly, right? Make it work at the speed of business, right? That's what I mean. Instead of having a model that's very, tedious, right, to enter all the inputs in, if we think about how do we practically get that to work faster and actually make it work for a market, we may have to think differently about how we deploy that or how we design some of these things. And scalability, right? When we think about any of these solutions, what are the supply chains? How are they manufactured? Quality control, right? That's always our challenge with some of these more quote unquote natural solutions, right? Is the consistency of whatever we're delivering. And especially when we get to the point of carbon markets, we need to have some sort of confidence in what people are buying and selling, right? So we need to have more dialed in, tighter expectations of what some of these solutions are. And then more broadly, I think we always got to keep an eye on the unintended consequences, right? I think that we can create a lot of challenges if we only focus on emissions reductions, right? Again, because then we're forgetting the bigger role that why animals are in our food system in the first place. We're forgetting issues like water that honestly, in some cases are more important, right? And more important for driving the carbon cycle than focusing only on methane. So bottom line, we think about sustainability and what you're going to hear today, right? This is a topic that's growing in importance. It's growing in importance, not just in the policy arena, the science arena, but in this ESG space. And I think this is something that's going to accelerate this topic and whether people are ready for it or not within animal agriculture in terms of corporate commitments rolling on down the supply chain. It's not an issue that's perfectly objective, right? And I'm glad that we have folks from all different perspectives here today in terms of the human nutrition side. That's incredibly important as well, because that's what we're doing. We're trying to nourish ourselves. And our real task is how do we take that 11% and shrink it, right? And create lower greenhouse gas emitting nutrient dense foods. So with that, happy to turn it over to the next speaker and keep us going. I think we'll take the questions later, right? But thank you all very much for your attention. Appreciate it.